Welcome to the new era of video creation with Bauzi 8. Today, we will discuss the concept of transfer learning. How would you apply it in a real-world AI project, and what are the challenges involved?
Here is the content. Transfer learning is a technique where a pre-trained model is reused for a new, but related task. Instead of training a model from scratch, transfer learning allows you to leverage pre-trained models, which have already learned useful features from large datasets. This technique is highly beneficial for tasks with limited labeled data. The primary goal is to leverage learned features, e.g., object recognition in computer vision, to speed up training and achieve better results with less data. It's widely used in domains like NLP, natural language processing, computer vision, and speech recognition, where large amounts of data are available for pre-training. Transfer learning is a game changer, reducing the need for expensive, resource-intensive training processes, especially for complex models like deep neural networks. There are several types of transfer learning based on the relationship between the source and target tasks. Inductive transfer occurs when the source and target tasks are different but related. For example, a model trained on image classification can be adapted for object detection. Transductive transfer is when the tasks are similar but the data distributions are different. For example, transferring a model trained on images of cats to images of dogs. Unsupervised transfer applies when the target task has no labeled data but can benefit from a model trained on large unlabeled datasets. Fine-tuning is the process of adapting a pre-trained model by adjusting its weights to better fit the target task. Fine-tuning is often used for deep learning models in NLP and computer vision. Each type of transfer learning depends on the similarity of the source and target tasks and data. To apply transfer learning, follow these key steps. Select a pre-trained model. Choose a model that has been trained on a large, relevant dataset. Popular choices include models like ResNet, VGG, for computer vision, and BERT, for NLP. Modify the architecture. Adapt the model to your specific task by replacing or adding layers, such as a new output layer for classification or regression. Freeze layers. Freeze the initial layers of the model, those that capture low-level features, to retain previously learned features, saving computational resources. Fine-tune. Train the remaining unfrozen layers on the new dataset. Fine-tuning adjusts the weights of these layers to specialize in the target task. This approach helps to leverage the rich, generalizable features learned from a large dataset and reduces the time required to train a model from scratch. Pre-trained models are available in various domains. In computer vision, popular models include ResNet, VGG, and Inception. These models are trained on large datasets like ImageNet and can be fine-tuned for specific tasks like object detection or image segmentation. In NLP, models like BERT, GPT, and T5 have achieved state-of-the-art results. They can be fine-tuned for tasks like sentiment analysis, text summarization, and question answering. For speech recognition, pre-trained models like Deepseek or Wave 2 VEC can be used and adapted for transcription tasks. Domain adaptation is another critical area, where a pre-trained model can be applied to domain-specific tasks, such as analyzing medical images. This ensures that the model retains relevant features learned during pre-training. Choosing the right pre-trained model depends on the task at hand and the domain you're working in.
Transfer learning offers several significant advantages. Reduced training time. Since the model has already learned general features from a large dataset, you can fine-tune it rather than training from scratch, leading to faster convergence. Improve performance. The model leverages pre-learned features, which usually result in better performance than training from random initialization, especially in domains with limited labeled data. Lower data requirements. Transfer learning can be especially useful when you have limited labeled data for the target task. The model can still generalize well by utilizing knowledge gained from a larger dataset. Cost-efficient, using pre-trained models reduces the need for computational resources, as you are not training a complex model from the ground up. TC benefits make transfer learning a go-to approach for many real-world AI applications.
Despite its advantages, transfer learning has challenges. Domain mismatch. If the source domain differs significantly from the target domain, the pre-trained model may not generalize well. For instance, using a model trained on general images for a highly specialized task like medical imaging. Negative transfer. In some cases, transfer learning might not improve performance if the learned features are not helpful for the new task. This is known as negative transfer, and it requires careful consideration when selecting the pre-trained model. Overfitting. When fine-tuning on a small dataset, the model might overfit. Techniques like regularization or early stopping can help mitigate this. Computational cost. Fine-tuning large models, especially deep neural networks, can still be resource-intensive, requiring significant GPU/TPU resources. Addressing these challenges requires careful selection of the pre-trained model and strategies to deal with overfitting and domain differences. Fine-tuning is a critical aspect of transfer learning. Here are several techniques used in the fine-tuning process. Freezing layers. Often, only the later layers of the model need to be fine-tuned. Freezing the initial layers, which capture basic features, preserves the general features learned during pre-training. Learning rate scheduling. During fine-tuning, a lower learning rate is often used to make small adjustments to the weights without disrupting the learned features. Early stopping. To prevent overfitting, fine-tuning can be stopped early when validation performance stops improving. Regularization. Techniques such as L2 regularization or dropout are applied to prevent overfitting, especially when fine-tuning on smaller datasets. These techniques ensure that the model benefits from transfer learning while minimizing overfitting risks. Transfer learning has found a wide array of real-world applications. Medical imaging. Pre-trained models trained on natural images are used for disease detection in medical images, even though medical images may be vastly different. Sentiment analysis. In NLP, transfer learning models like BERT can be fine-tuned to understand specific sentiments in text, which is invaluable for businesses monitoring customer feedback. Autonomous driving. Pre-trained models in computer vision are used for object detection in autonomous driving, detecting obstacles, pedestrians, and vehicles in real time. Speech-to-text. Pre-trained speech models can be adapted for different languages or domain-specific speech recognition tasks. Transfer learning allows the application of cutting-edge AI to a broad range of industries by reducing the resources required for model training. In conclusion, transfer learning is an invaluable technique for many AI tasks, providing faster model development, improved performance, and lower data requirements. Best practices for applying transfer learning include: carefully select relevant pre-trained models that align with your task's requirements. Continuously experiment with different models and fine-tuning strategies, as the first model may not always perform the best. Monitor performance over time and update the model as needed to adapt to new data. Tackle the challenges of domain mismatch, overfitting, and computational cost by using appropriate regularization, learning rates, and model evaluation strategies.